Joint work with James Lemay and Priya Srinivasan, and it's based on an archive paper we've got there. Unfortunately, the archive paper is 8 pages long, so I'm going to sort of pick and choose my way through it. Here are the authors. The important one is me in a hat, and the beautiful one is Priya. And the one grinning at you is of course JS. Drazin, Michael Drazin was a British ring theorist who worked at Purdue. He was born in 1929, and I believe he still lives. So if anyone knows him, we were trying to get a photograph of him. So please let me know. His paper about this was in 1958. And here's the definition. It's a very simple idea. X has a Drazin inverse, and we write this X to D. If there's a natural number k, such that X raised to the power k plus 1, followed by the Drazin inverse, has its power bumped down 1. So two other things, that the Drazin inverse, when you surround X by the Drazin inverse, it reduces it to the Drazin inverse, and the Drazin inverse commutes with X. A Drazin inverse, of course, may not exist, but if it does, it's unique. We want to talk about Drazin inverses and categories, and the definition may seem a little bit disappointing, in that, in fact, you just talk about Drazin inverses of endomorphisms. And again, it's just that there is a k, such that when you take X raised to the power k plus 1, and follow it by its Drazin inverse, you knock that power back down 1. And then the two other parts, which says the Drazin inverse always commutes with X, and when you sandwich X between Drazin inverses, you get the Drazin inverse. There could be, of course, many k for which this works, but there's going to be at least k for which this works, and that's called the Drazin index of X. An object is Drazin if all its endomorphisms are Drazin. And a category, on the other hand, is Drazin in case every object is Drazin. Every category has a Drazin subcategory consisting of the full subcategory of its Drazin objects, of course. A simple example is sets. In sets, every finite set is actually a Drazin object. And so the category of finite sets is Drazin. And in fact, more generally, every finite set in rich category is Drazin. So there are lots of examples just from that. When X is Drazin, note that X followed by its Drazin inverse is actually an idempotent. And when that splits, we'll talk about split X being split Drazin. Okay, so what I just walked through the proof that Drazin inverses are unique. Inevitably, there's going to be a step which requires induction. So the first two things of this lemma are very simple. It says when n is greater than or equal to the Drazin index, then when you multiply by the Drazin index, you just bump the index down. So, and indeed, when you bump it down by m things, so long as you're above the Drazin index, you can knock off powers. You're worried about me. Okay. Yeah. And the last one is the one that requires the step by induction, and that is that xn followed by the Drazin inverse raised to the power n plus 1 for all n, is the Drazin inverse. And you start off with the initial step when x is raised to the power 0, which is immediate, and then when you raise it to the power n plus 1, you get x to the n plus 1, followed by the Drazin inverse to the power n plus 2, and then you just split off an x on the front and a Drazin inverse on the other end, and get rid of the thing in the middle, and you're left with x Drazin inverse and x Drazin inverse. You use the commutativity to get the sandwiching, and you're done, back to x to the d. And then, and that allows you to prove the uniqueness, and the proof is down below, that you use that third step from the Drazin inverse, getting to x to the n, x d to the n, where n is something above the index, the Drazin index, and then if y is another Drazin inverse, you can turn that into y followed by x to the n plus 1, and then again what you can do is split off an x from the front, and then you get the x to the n followed by the Drazin inverse to the n plus 1, and that collapses down to x to the d, and then you get this symmetric expression in y, x, and x to the d, and then essentially you reverse that proof to get back to y. Okay, so one of the most obvious things, but also one of the most important things about a Drazin inverse is it's absolute. So it's preserved by all functors.
I'm a little bit worried about you. You're very close to me.
I know where. Okay. So keep the edge of your seat, you know. Okay, so some basic examples of Drazin inverses are, well, an inverse is a Drazin inverse, and it's a Drazin inverse of index 0. Every idempotent is a Drazin inverse. It has index 1, and the Drazin inverse is the idempotent itself. More interestingly, in any category of matrices over a field, if you take a block diagonal matrix where A is an invertible matrix and N is a nilpotent matrix of degree n, then M, the combination, is a Drazin with index, the nilpotent degree n. And the inverse is just the block diagonal matrix with zeros all around the inverse of the A. So this little example allows you to construct maps which are Drazin of arbitrary degrees, because it's very easy to get a nilpotent matrix of degree n using other triangular matrices. Okay, so one important thing is that Drazin inverses don't compose. And let me just walk through this. So a function, so we're going to work in sets. So we're going to give you an example in sets. A function from n to n, which is strictly increasing and order preserving, cannot be Drazin. So that's the first thing you observe. So suppose it is Drazin and f to the d is Drazin inverse and its index is k, then let's look at f to the k of 0. Well, because it's Drazin, that's the same as f to the d followed by f to the k of 0. And then because f to the d commutes with f, you can and you can move the f to the d in, and you get f followed by f to the k followed by f to the d. But then, because you're strictly increasing, you can knock off that front f, and you know you'll get something strictly bigger, which is f to the k, f to the d, to the 0. But the point is that f to the z0 is at least as big as 0, because 0 is the least thing, so that is greater than f to the k of 0. And so you get a contradiction there. And now, to give the example, you just take two idempotents. One idempotent given by taking the even numbers and bumping it up by 1 and leaving the odd numbers the same, and the other idempotent by bumping up the odd numbers and leaving the even numbers the same. And then if you compose those two things, you get a strictly increasing and order-preserving function. So it's not Drazin. Okay, so to be a Drazin inverse, that is x to the d for some x, actually means that your Drazin index must be less than or equal to 1. And in fact, x to the d to the d is equal to x to the dx. It's easy to check this. And if x is Drazin, then if you apply x if you Drazin invert it 3 times, it's the same as Drazin inverting it 1 time. And in fact, a map with Drazin index 1 is the same thing as a group inverse, which is a more familiar notion. Being a group inverse is actually totally the same as having Drazin index 1. And the point is that if you are a Drazin index, you have Drazin index 1, so you are a group inverse at that point. There was an earlier definition of Drazin, which was given by Azumaya, and he called it strongly pi-regular rings, in his 1954 paper. And it uses left and right pi-regular, and he proved that a fully pi-regular thing, which is both left and right pi-regular, is the same as being Drazin. So left regularity means you've got that bumping off property. So y followed by x to the k plus 1 is x to the k on the left, and right pi-regular is you do the same on the other side. And fully regular is when you're both left and right pi-regular. And that's actually equivalent to being Drazin. So the point is, this is a slightly simpler way of describing Drazin things. But what's nice about the way Drazin expressed it is it's more structured. So it told you that there was an idempotent sitting around there. And it commuted with its Drazin inverse, and there was a Drazin inverse, which is unique. So although Drazin maps do not compose, we do have the following property, that if x is Drazin if and only if x to any positive power is Drazin. And in fact, the Drazin inverse of the positive power of x is the same as that positive power applied to x to the d. So, and there's also these things have been known for a long time, and also there's this naturality result that if x f equals f y, and x and y are Drazin things, then that implies that you get a square commuting on the right, where you replace x and y by the Drazin inverse. And in particular, that means that if you have a Drazin category, then any slice category of that category is Drazin. Just by setting y to the identity, and of course co-slice is by setting x to the identity. Tom Leinster introduced the idea of a map having an eventual image duality. He was looking at dynamical systems, and he wanted to characterize the sort of eventual behavior of the dynamical system. And so what he did is he took the doubly infinite sequence of x's and looked at the limit and co-limit and said that you have eventual image duality if the canonical map from the limit to the co-limit was an isomorphism. Obviously a map need not have eventual image duality, and if it does, it need not be absolute, so there are functors which don't preserve eventual images. However, it's worth noting that in any category, if x is Drazin, then x has absolute eventual image duality. And so any Drazin category has absolute eventual image duality for every map. So it's a very strong property. Okay, so I'm going to show you how we actually were able to show that lots of categories are, in fact, Drazin categories. And to do that, what we looked at was the rank, a rank functor. So into a little two category, and in fact the two category is the span category of the natural numbers with the canonical order. So explicitly the naught cells are, well, the natural numbers. The one cells are just, well, spans, so the m is less than the minimum of n1 and n2, and the composition is just by taking minimums, and the two cells are just use the natural order and the natural numbers. And then a category has rank in case there's a collax functor into this little rank 2 category. And a category has expressive rank if it satisfies two properties. The first property is that it's got to reflect isomorphisms, and X has got to have a factorization system, and we say it expresses rank in the sense that for every F, the rank of F is the same thing as the rank of the E part of F, and it's also the rank of the part of the M part of F, and it's the same thing as the rank of the image of F. So, and then you can prove it with a little bit of work. Whoops. Oh, no, hold on. Yes. With a little bit of work, you can prove that any category with an expressive rank is Drazin. And and here are a series of examples of that. So finite sets is a Drazin category because the rank is actually given just by the size of the image of the function. Finite dimensional matrices over any field has rank, where rank is given by dimension. And, finite dimensional matrices are equivalent to finite dimensional vector spaces. And in fact, being Drazin is preserved by equivalence, so finite dimensional vector spaces are Drazin, and in fact it's just the rank is dimension. A more complicated example is the category of finite length modules over any ring, including a non-commutative ring. And the rank is just the length, and that works. And that example underlies what are commonly called fittings lemmas in non-commutative ring theory. One of the sort of categorically one of the slightly unsatisfactory aspects of Drazin inverses is they just work with endomorphisms. But you can actually sort of bump this up, deal with opposing pairs of maps. So Chris talked about this as a category. So here we're just like an opposing pair is just a map F from A to B and G from B to A. And then you can have what's the Drazin inverse of an opposing pair of maps. And it consists of a pair, F, the Drazin inverse of F over G, and the Drazin inverse of G over F. Right, the G and the F determine the direction over. And then you just have to write down the same things, but it's slightly different because, I could point, right, because you're just knocking off an F, although you're building up both F and G, the composite FG, and here you're knocking off a G like that. And then you have the analogous requirements and a commutation requirement. Well, it isn't quite a commutation because you flip from F to G and back again. And then you can prove that Drazin inverses of opposing pairs are unique and of course absolute. So it's still oops, sorry. Okay. Now you can relate this back to ordinary Drazin inverses using what's known as Klein's formula. He used it in 1965, so this is all very old work. If you have an opposing pair, then FG is Drazin, if and only if GF is Drazin. And one then observes that having a Drazin inverse of an opposing pair can then be expressed by ordinary Drazin inverses. So the Drazin inverse of F and G is the pair where F with Drazin inverse over G is G followed by the Drazin inverse of FG, and G Drazin inverse over F is F followed by GF to the D. And then you have that obviously a category has Drazin inverses of opposing pairs if and only if it is Drazin, where you go back by observing that the pair X with the identity, when you take the inverse out, you get the Drazin inverse out as the first component. So, Chris promised something about dagger categories, so here it comes. So what got us into this work was actually JS and I wrote a little paper about more Penrose dagger categories to try and give a sort of more categorical intuition behind that. And Priya then pointed out that there were these things called Drazin inverses, and that got me going on trying to understand Drazin inverses, and that resulted in the paper expanding from a sort of 5-page thing into an 80-page thing, as we sort of pulled in all the results about Drazin things. So the point is that in a dagger category, there is a natural opposing pair where you take F and F dagger going in different directions, and so there's a natural sense in which you can say it's in which you're interested in it being a dagger category. So the more Penrose inverse of a map in a dagger category, I've written it as F circle, and it says that if you have F from A to B and F circle, then F circle F is equal to F, and F circle F circle is equal to F circle, and then you have a sort of commutation relation, except it isn't quite a commutation relation, where F circle dagger has got to equal F circle F. And then the theorem is that in the dagger category, F has a more Penrose inverse, if and only F. The adjoint opposing pair is a Drazin inverse, so you can characterize more Penrose inverses. Well, okay, I better end. And let me remind you that the archive paper has proofs and references, and I haven't discussed a whole bunch of aspects of this. In particular, I haven't discussed how it relates to the idempotent splitting of things. A very important thing, and this takes you really into the ring theoretic applications, is the core nilpotent decomposition of Drazin inverses in additive categories. So in fact, that matrix example I gave you was an example of that decomposition, but it's totally general. And in additive categories, there are lots and lots of characterizations of Drazin inverses, and we didn't do that. And I didn't chase through the business of what the relation to fittings was. And that's it. Thank you very much.
We have time for a couple questions.
Yes.
So I've been interested in kind of taking, let's say, the theory of groups and then making the theory in a balance to a balanced theory. So meaning that I don't want the variables to disappear. So when you take an inverse of you have the inverse axiom, in the equation you kind of lose the variable. So this kind of talks about defining the notion of an inverse kind of in a balanced way. But if you add axioms like you would like the notion of the inverse to kind of be this kind of a homomorphism or anti-homomorphism. So if you add these axioms to the setting, have you worked with these inverses in settings where it respects composition? I mean, like, does it trivialize it too much, or do you have interesting examples of those?
Well, composition is preserved by the Drazin inverse, right?
I mean that when you take this inverse of a product, it's not the same as the...
wait, so of course Drazin inverse is the absolute, so any functor preserves them, right?
Yeah, but let's say if you take the more inverse, and you are in a category, and you take the composition of two, and you take the more inverse, then it doesn't respect the...
Yeah, it doesn't respect the composition.
But if you add the axiom...
But it should, what do you get, yes. And don't know. Don't know. But it doesn't seem to happen very often. That's,
but in group voice, for example.
Yeah. Well, in group voice it does, yes. Yes, there are some basic examples which do.
One more question? Oh, there's...
For like linear operators between two spaces, do you have any idea what could be a Drazin inverse?
For what?
Do you have any idea maybe, or like between linear operators of like, super spaces? Do you have any idea what it could be like a Drazin inverse? Could be maybe like a compact operator or something like that?
Yeah, actually the example of it turns out to be one of these block categories with a nilpotent block. Up to an isomorphism acting on either side, you get an inverse block and a nilpotent block. And that's the core nilpotent decomposition that you always have in an additive category. So.
So let's thank Robin again.